I thought I would go over, start by going over some bits of comment that are related to last time. So you'll recall that we were talking about three coloring. And that in the three coloring rule, I'm going to be using the colors red, blue, and green. But we could use 0, 1, and 2 or whatever we liked. And the rule for three coloring is 3 or 1. That's the rule. And what that rule means is that you're coloring the edges of the diagram, and you color it with an X and a Y and a Z that are in R, B, and G. And so you must see that X, Y, and Z together form three colors or just one color. That's the rule for coloring the diagram. So then you can ask, can I color a given diagram? And of course, in the case of a simple trefoil diagram, we're coloring the arcs, right? We color the arcs in the diagram. So in this case, for example, I could color this arc red and this one blue and this one green, right? This whole arc is green, this whole arc is blue, and this whole arc is red. And then what I'm asserting, and I just thought we'd go through it again and then talk about the structure of it. What I'm asserting is that, that when you do a Writhe move on the diagram, then you will automatically induce a coloring on whatever extra arcs that you produced in doing the Writhe move. And you can see this in the abstract quite easily. Let's just do it in the abstract for a moment. Suppose that I have an arc like this. Oops, try again. Okay. Yeah. Suppose that I have an arc like this, and it's colored red. And I do a Writhe move and turn it into this. Well, what I have in mind is that I want to keep red here and red here, where it might be touching some other part of a larger diagram, and still color everything in here. And there's no problem at all. I just leave it as it is. It's red, and that's one color at a crossing, so one works, right? Good. So that's Writhe move number 1. Now, what about Writhe move number 2? In Writhe move number 2, I have two colored arcs, and I want to induce a coloring after I do the move, like this. So if this was red and this was blue, of course, that's not the only case. It could be red and red. They could be different or they could be the same, but I'll just do one case and leave the other for you. Then afterwards, this is all red. Here I keep blue out here and I keep blue out here. And then no problem, compatibly, I put a green there, and I have three colors at this arc and crossing, and I have three colors at that crossing, and everything works fine, right? But you will notice that, that if I went this way, I would lose a color locally, right? If I went the other way, I would have, I might have a color here, and a third color in the middle, the little arc, and when I pulled it apart, a color would disappear. Could happen. All right, but nevertheless, I can go either way and induce colorings from one diagram to the other. And then we want to look at the third Writhe move, and I'll try doing it here near the bottom of the board. I hope you can see. So then I have a before and after picture that I'm going to be thinking about, right? Here's a before picture for a third move, and then here's the corresponding after picture for that third move, like this. And now let's put some colors on this one. Suppose I have red and red, And then this would have to be red, and maybe I have green here, in which case red to green would give me blue, and green to red will give me blue, and red is down here, like that. Now what I want is that all the colors on the outer lines should remain the same. So I want red, red, green, blue, red, and blue out there, because I'm imagining that I don't change the coloring in a larger diagram. I'm just going to change it from this. And then do I get a compatible coloring here? Well, red to blue has to be green, and green to red has to be blue. So I can just say, okay, right? It's unique. And similarly going the other way. And this is one case among many, and you could check the other cases yourself and find that it all works out. So this tells you that Reidemeister moves cause inheritance of colorings. All right, so that's a good thing to know. And then you might worry about this losing a color thing, right? Let's think about that for a moment. What happens with this losing a color thing? I'll work up here on the top of the board. I was going to just do an example there in the middle, and I will, but let's not run into it. So I'll just give myself space up here to draw. If I had gone and colored two circles like this, then we would have perhaps red and blue, and green is in the middle, right? And when we did this move that I was just showing you, oh, I don't. Oh, maybe I'm supposed to select something. Maybe. Red and blue. And we genuinely did lose green, right? It can happen. So you could have with a link, you could have the situation that you have a three-colored link. Genuine, when I say three-colored, I mean three colors are really there. And when I pull it apart, I lose a color. Could happen. It's important for links. So links can lose colors. But I say that a knot diagram cannot lose a color. If it's colored with three colors, you're not going to be able to make it lose a color. And here's why. Suppose that you had a situation where you thought you were going to lose a color, right? Red here, blue here, green here. But then it's a knot diagram. So somewhere up here, this, if you keep on going, turns into this, but it must meet somebody in the course of that. And we'll end up here, and then this will end up here. That's not a very, that's not a great example. Maybe I should make a real example. Let's make a real example so you see what I'm saying. What I'm saying is that the diagram is connected. So let's draw a knot diagram where you might lose a color and it's actually a knot diagram. So let's say that we have this in it. And it's actually a knot diagram. So if that means I have to go, I can't just come back here. I have to go through this one as well, right? So sooner or later, I'm going to wander through this one, and maybe I go here, and I end up over there like that, right? Something like that, right? And suppose that this arc here was red, and this one was blue, and we don't know anything, and then this would have to be green, right? And we're worried that we would lose green. But you see, as you walk from here over to here, you change from red to blue. And you say, how can that happen? How can it happen that it was red here and it turned into blue over there? You have an arc and you're walking along and this arc is red, but after a while, you're just walking along the arc, it turns into a blue arc. How can it happen? By the rules, the only way it could happen is if it met green. That's the only way that red can turn into blue. It has to meet a green. So that means that the answer is there was a green out there somewhere. So then the situation schematically looks like this, that you went from here to here, and at some point you met green. You were red here, you met a green out there, you turned into blue, and over here there was a green. So when you did the Writhe move down here and lost that green, you wouldn't lose the other green. So in order to have red and blue, you needed a green somewhere else. And so when you lost this green, you didn't lose all the green. And if you wanted, we could see whether, I don't know whether this is going to color up correctly the way I said. Maybe it won't. Let's see. Let's just color this and see what happens. If it will color at all, it might not even color 1, 2, 3 crossings. No, it should color, but maybe not the way we want. Red, red, this would have to be green. Blue, sorry about red. Sorry. Red meets red gives you red. Red meets red gives you red. And blue, green, red, this is also blue. So blue and red would make a green here. And this was a blue coming in here, and a green and a blue made a red. So this is not a real example, but we could easily make a real example. A real example could happen right here, for example, and we might as well look at it. All right, but you understand my argument. The argument is very simple: that if we have one component, and then in order to lose a color under the 2 move, you would have to change one color to another color by that color, and that color must be somewhere else. And so what we conclude from this is, for knots, once 3-colored, then always 3-colored. Okay? No matter what I do to it, it'll stay 3-colored. And so now we can look at the example and see all that happening in the example. So here's red and blue and green here and green here, and green met red to become blue here. Okay? So that's doing one move. Let's do it again. So now I have red and blue and green. Oh, careful. Red, blue. Here's the green. Red and blue together make green. Let's just color it. Blue and green make red. And this is green coming out here, which comes in here, green. And this is also green, and green and red made blue, and blue and green made red. So now if you look at it, you see that what happened was that the blue bumped into the green and made red there, right? And then I'm going to push it through here. Let's see, let's just work on this diagram rather than draw another diagram, right? So let's suppose that I now wish to take this, which is red here, and we push the two reds this way. And they bump into red, so they're going to be red, and I'm going to keep on pushing them up here. So these two are red. And then this becomes red, blue, green. Okay. So you see, I'm making more and more complicated diagrams, and they're all getting three colored. And our theorem says that no matter what complicated diagram you produce from the truffle knot, it'll still be three colored. And we can, let me erase that green there. Put in somewhere else over here. I want to do a three move. And this three move is this one right here. So I'm going to erase this, reroute these a little bit. Like that. Now let's see, what was green to blue? This was the red. All right, and so now we should see it all working compatibly. Blue meets red and becomes green, and green meets blue and becomes red. That's okay, right? So there we are. That's an example of it all happening on one diagram. And never in any case while we're doing this do we lose any colors. And there are infinitely many diagrams of the trefoil knot. And we proved a coloring theorem then. If you can draw some enormous diagram of the trefoil knot, and it will be three colorable. We've proved it by induction. Okay. But let's continue with three coloring a little bit further now. Can you three color this diagram? Why don't you try for a moment? Take a pad of paper, draw the diagram. This is the figure eight knot. That's its name. It's called the figure eight knot. I'll put a table of knots into the Google Drive for you later today. And then you'll see that this is the second knot on the table of knots. If you were going to make the figure eight knot, I'm giving you a little time to try coloring it. If you're going to make the figure eight knot, you'll see why it's called the figure eight knot. Because to make a trefoil knot, you make one turn in the rope and drop the rope through the turn, and you get a trefoil knot. If you make another turn in the rope and drop the knot through, you get the figure eight knot. And oops, I turned it the wrong way. Let's do it one more time. Like that. And as you see, it looks like the number 8. That's why it's called the figure eight knot, as far as I know. But you can't color it. Did you try? Let's try. Suppose I say red here. Oh, with 3 colors, of course. You can color it with 1 color, but let's try red, blue here. Red, blue here, two distinct colors. This would have to be the third, green. Green comes all the way over here. red and green are here. Red and green mean that this should be blue. But blue and blue mean that this should be blue. And that doesn't work because it's red. So it wraps back on itself and refuses to be three colored. Just doesn't work. Sad. Well, not sad. Some knots can be three colored and some can't. But that leads to the question, when? And in order to answer that, we need to generalize what we're doing so that we understand it better. But obviously, you can ask the question, when can I three color something? And even at this level, without knowing more, we can see some things. For example, suppose you had a little three twist, like that. And suppose you had colored this with two distinct colors. Then let's try it. Blue, red, red and blue make green. Blue here. Blue and green make red. Green here. Green and red make blue. And red here. And we see that we have a little black box here. And if you have a blue and a red coming in, two distinct colors coming in, then two distinct colors can come out. And the same could be true if there was no twist at all. Then you could have blue and blue comes out, red comes out. So that tells you that if you have a knot without a three twist in it, that's three colorable. You could put a three twist in it, and it would still be three colorable. So we can make lots and lots of knots that are three colorable from given ones by adding or subtracting three twists. Okay. So that's interesting. What does this tell us about the figure eight knot? This implies that, let's call this knot E for figure eight knot. And let's call this one T for trefoil. This implies that E is not equivalent to T. They're different knots. All Writhe moves can carry E to T. Think through the argument, right? It's a very simple argument. If you could carry the trefoil knot into the figure eight knot, you could push it and keep the colors going, and eventually you'd have a three coloring of the figure eight knot. But you can't color this, and therefore there's no way to get to the figure eight knot from the trefoil knot. So we now have a little bit more results about knot theory. We have that the trefoil knot is knotted. We have that the figure eight knot is also knotted. Oh, wait, do we? Have we proved that it's knotted? We've proved that it isn't equivalent to the trefoil knot, but we haven't proved that it itself is knotted. Maybe it's equivalent to the unknot, right? The unknot. Right, so we haven't quite proved that it's knotted yet, but we know it's different from the trefoil knot. We're going to have to work harder to prove that it's knotted. All right, now I want to show you one more thing I can do with the three coloring. Let's look at the Whitehead length. Can you three color the Whitehead length? It's called it W. Well, again, you can try and see. Let's just do it together, right? So Of course, you might want to consider other cases, but I'm going to assume that right here, there are three colors. So I have red, blue, green. And now let's see if this can be extended to a three coloring of the whole length. So green propagates all the way over here, and red propagates all the way over here. And this blue comes down here, and red and blue, let's see, blue here, green here, that makes red here. So it all feeds back together like that, but red and green make blue. And red and blue make green. And blue is not equal to green. And that implies that W is not recolorable with a little extra work. I'll leave the extra work to you. You could say, well, what if these were the same color rather than different colors, right? And what would then happen? And you'll find that you then propagate. If you make these the same color, you just make the whole link one color. So that's not interesting. So there's no non-trivial three coloring of the Whitehead link. Can we conclude something from this? What do you think? Think about it. Suppose W is equivalent by Reidemeister moves to the trivial length. Then the trivial length would be equivalent by Reidemeister moves to W, because you know Reidemeister moves go in both directions, right? So there would be a sequence of Reidemeister moves from the trivial length to W. Now, color the trivial link. Then you would have red and blue, for example. And then induce colorings. And you, by Reidemeister, by those same Reidemeister moves, and W would have a non-trivial recoloring. It would have at least these two colors, right? Because you started by coloring the trivial link with two colors and you start pushing it around. You can see how that would go. Just like in the previous slide, red and blue, and we push one underneath the other, and now you've got a green, and then you push it under, and you get a red or a blue, and you keep on going. And every time you do it, you are getting some coloring, and it'll never go down below 2, because if it went down below 2, then when you went backwards, you'd only have one color here. So it's got to have at least two colors, but it doesn't work. And so this implies that W is not equivalent by Reidemeister moves to the unlinked. It implies that W is linked. So we can use the three coloring to prove that the trefoil knot is knotted, and we can also use three coloring to prove that the Whitehead link, which had 0 linking number, remember from last time, is actually linked. We can use it to prove that. Isn't that neat? That's an amazing argument. I'm sorry, I can't remember now the author of that argument. I'll tell you next time. There's a non-theorist who thought that argument up. So you see, you could try that out on some links that you would like to prove that are unlinked. You can show that a link is linked if you can show that it's uncolorable. That's what you can do. Whereas if you show that a knot is uncolorable, you don't conclude much from it, right? But if you show that a link is uncolorable, yeah, then it's linked. And so here's an exercise. Let's put it on this board, and I'll leave it to you to check. Prove that the Borromean rings are linked. Now remember what the Borromean rings were. Borromean rings are these three. If you remove any one of them, the other two fall apart. And how are you to do this exercise? Well, show that you can three-color it. So that's an easy exercise if you would do it, but it's instructive to do it, right? You try it out. You put some colors on the lines and follow out where those colors are forcing things to go. And you find that you get a contradiction if you try to color it with three colors. Can't be done. And that proves that the Borromean rings are in fact linked. Other exercises that you can do, you can make up yourself if you would try. So I suggest you do that. Try some other links and see what you can do about that. I want to show you one more application of the three coloring. It's a general theorem. But I have to say what my theorem is about. So up here. Oh. Okay, that's right. Here, there's something about writing in the upper part of the board, and it gives it trouble. Maybe it's just giving trouble. I have a knot, and I have another knot. And I put them together along a line like this together, all right? So here's K and here's K prime. And this new knot, this is called K connected sum K prime. Connected sum of knots. All right. So that's an interesting operation that you can do. If you have a knot, you have another knot, then you can form their connected sum. The way I think of this, if I think of knots as closed loops, is like this. Here's my knot K. And I think of having a little arc for it. And here's my knot K prime. And the closing arc for it over here. And then what I'm going to do is I'm going to cut a little arc out of that, cut a little arc out of that, and put them together like this. And have a way of adding knots. Okay. And it turns out that it doesn't matter where you cut them and put them together, you get the same knot. I leave it to you to think about that it is well defined. You just take two knots and do that. And of course, it corresponds to something that you can very easily do with rope. You have a rope with two ends and you tie a knot in the rope. And then you tie some other knot in the rope. And now you have the connected sum of those two knots. So now comes a very nice question. Is it possible to take a knot and another knot and put them together on the rope in that way to form their connected sum in such a way that the two knots will cancel each other out? It could happen, maybe, right? I put them together and then I'm allowed to push them around any way I like and try to see whether I could make them disappear. Well, I can make them kind of get involved with one another, but then they seem to come back apart, and they don't disappear as far as I can tell empirically. Trying it with rope, you could try it with rope yourself. You'll find it doesn't happen, and the theorem tells us that it doesn't happen. The general theorem is that if K and K prime are knots, and if K connected sum with K prime is equivalent to the unknot, then K is equivalent to the unknot and K prime is equivalent to the unknot. Now that turns out to be a little harder to prove than you might think. But I'm going to show you two proofs. One of them is specialized to colorable knots. We can easily prove that if K is three colorable and K prime is any knot, then K connected sum with K prime is knotted. So in other words, if you have a three colorable knot, there is no way to cancel it with any other knot. So in particular, that means that we can prove that if I have the trefoil knot and I hope to cancel the trefoil knot by adding some other knot on the rope and putting it together with it, can't be done. Any other knot, doesn't have to be three colored, it could be like this, figure eight knot. And what's the proof of this? Well, let me illustrate with the trefoil and then you'll see exactly what I'm talking about. Let's take the trefoil and let's take the three coloring of the trefoil with a red here and a blue here. Then we get a green here, and then blue and green come together and make red. So you see, if you cut the trefoil, then the input arc and the output arc have the same color. And now I have some other knot. And now I come back to where I started. And I color the other knot with that one color everywhere. That's okay. One color rule, right? Just take the other knot and color it all red. But then this total knot here, this is three colored. Right? All the three coloring is concentrated in the trefoil in this diagram, but it is three colored. And that implies that this knot here, let's call it K double prime, that implies that K double prime is not equivalent to the unknot. Because anytime you have a non-trivially colored three knot, it's not equivalent to the unknot, it's not. So I can't, so the fact is that I can't remove the three coloring of it by adding another knot. In fact, I just extend the three coloring of it by adding another knot. And so if I have a three colored knot, then there's no way to cancel it. And that's the proof of the special case of the general theorem that you can't cancel knots. In the interest of time for today, I'll tell you a proof of the general theorem later, but this coloring lets you prove it in the special case. Okay, so let's see. That's one comment from last time without going further. And now another comment from last time has to do with definitions of equivalence. If we have a knot or link thought of as curves that are embedded in R3, and we have the pair of spaces R3 and the containing subspace of the knot. So we're thinking of it sitting in space like that, topologically, not worrying about diagrams. Then we say that R3K is equivalent by homeomorphism to R3K prime if there is a homeomorphism H taking R3 and H restricted and applied to K gives us exactly the set of points K prime. All right, and talk about oriented equivalence if H is orientation preserving. Right? So this was maybe the original definition of what it meant for two knots to be equivalent. Here I haven't talked about using a sequence of pictures of the knot which go slowly from one to the other, an isotopy. I've just said there should be a homeomorphism which throws one to the other. For example, in the case of unoriented, we could have H of XYZ is equal to X, Y, and minus Z. And then if you had a knot like this, and I'm thinking of the Z direction going up that way, then you could, under H, you see that would change this direction, and you would end up with a mirror image. That. So, knots are equivalent by homeomorphism, not oriented to their mirror images. Okay. So then there is a theorem, and I'm not going to prove it, so I should give you some reference about this. I'll look to see what I can about the relationship between this and the other way that we're thinking about it. But Oriented equivalence by homeomorphism is the same as ambient isotopy, which I mentioned before. And remember, ambient isotopy means that you are looking at putting this inside, that you're going to have a series of pictures. You're going to have case of t, that would be k0. You're going to have case of t, where t belongs to 0, 1, the interval 0, 1, and each one is an embedding, and you go from one to the other continuously. And then I should have said for ambient isotopy, usually differentiable, non-zero tangent vector. So you should think of this as a curve in three-dimensional space, which has a derivative. All the coordinates of it have a derivative. And when you form the tangent vector, it's non-zero. And then you go through families that always have that property. And that will make sure, this will make sure that you cannot shrink the knot to nothing. Because we don't want to shrink the knot to nothing. But you could imagine that as part of an ambient isotopy, the way I had described it before, if I didn't put a control on that. In other words, consider the following family of knots. I make a nice trefoil like this, all right? And then I say, okay, now here's an isotopy of the trefoil, and I start shrinking it, right? And now at this point, I start making it smaller and smaller and smaller. And in the limit, it just disappears. And at every stage, you see a picture of an embedded curve, right? All the way to the end where there is no knot at all. Each one is an embedded curve. So, and everything is happening continuously, and I don't want that. So I have to put some control on my isotopy to make sure that the knots don't just disappear like that. All right. And my favorite way of doing that is differentiable, so that we can't make the tangent vectors all stay non-zero if we did something like that. But then that oriented equivalence is the same as an ambient isotopy requires some work. But throwing a knot by a homeomorphism from one picture of it to another picture of it is often exactly what you want for thinking about it. In the case of the unoriented move, there is no ambient isotopy that takes you from here to here. There is no set of Writhe moves that takes you from here to here. We have to prove that, but it's true. Let me think. Right. Another version of ambient isotopy, Writhe version of ambient isotopy. Writhe version of ambient isotopy is for piecewise linear knots. So his knots are all made of straight sticks, like this. imagine that in space, okay? I've probably drawn it so it could be realized by straight sticks in space. And that's a knot for Reidemeister. That's the kind of knot he was interested in. And you can represent all your knots that way. So if you think of knots that I make with a rope, you can approximate them by using straight line segments. But on the other hand, if you start making knots out of straight line segments and ask what's the least number of segments that you can make a knot with, then you have another kind of problem, which we can come back to. But he's willing to use as many segments as he likes. And his 3D move is the following. You're going along and you have one of those segments. And you take a point in space here. And you look at this triangle. And you replace this edge by the other two edges of the triangle, like that, or the other way. You have two edges of a triangle, and you look at the third edge and cut these out and replace that by that. And then the stipulation is no edges of K can pierce the triangle. Very important. Must be the case, okay? So you see this triangle. And you must never have any other edge of the knot going through that triangle. It could go over it when you're looking at it, and some things are layered, could go passing over or passing under, but it mustn't go straight through because you could change the knot type if it went through. But if nothing goes through, then this is an isotopy of the knot, which starts here, and you can think of slowly moving it until it ends up here, right? It's all fine. So that's his basic isotopy, Reidemeister's. And then Reidemeister proves the theorem by examining projections of EL knots under the triangle move. So when you make a projection, there might be other lines going over and underneath the triangle. You think about what happens when you do that. Now, whether or not I tell you more about that depends on how much time we have today. I'm going to spend 5 or more minutes on it, but we could come back to this. It's quite an interesting subject. So let's consider a lemma. Let me illustrate the lemma and then you'll see what I have in mind. Here is an edge in a PL diagram in 3 space, right? And here's a very nearby point. And here's a triangle. Now, if the point is sufficiently nearby, there certainly won't be any other edges going through it, right? We can avoid them all. They're just happening. There are a finite number of them. We can avoid it. And so this will be equivalent to, this. Okay. Now I'm going to put another point here and look at this little triangle here, like that. That little point is a point that was back over here on the straight line that I was dealing with before, but it isn't there at present time. There's no vertex there, okay? But I put that point out in space, and then I'm allowed by Writhe to replace by these two edges and then go over. This becomes an endpoint, right? Edges have endpoints. And then I can do the same thing on this little triangle on the right, and I end up back where I started with an endpoint in the edge. So this lemma says that I can start with an edge. I can do a nearby triangle. I can go through making two edges and then making two edges that are making an edge that goes right along the original edge and then making another edge that goes right along the original edge. And I can go all the way over to here. So that means that the lemma is any edge can be subdivided into two edges. You can put a point in the middle of an edge. It looks like a kind of football, but it's true, right? And since that's true, that means that I can assume I can take my piecewise linear knot and I can make it have little tiny edges whenever I want to. So that means that I can subdivide everything and make it very small. And because of that, now I'm going to jump. You can think about it. Because of the lemma, we can consider very small triangles. Now, I'll leave it to you to sort of suss out how you would make your triangles very small, but it's just a matter of cutting everything up into smaller pieces. And then you can ask, well, what do small triangles, what do projections or how do projections of small triangles appear? So we have this knot up in space and we're projecting it down into a plane here. And down in the plane, we're going to have some diagram made out of straight lines in the plane like that, right? And a triangle move up here is going to turn into a triangle move down there. So, so I give you an example. You might have a triangle like this. Now, where are the dotted lines? So I suppose that that's going to be my dotted line. And then over and under, well, yeah. So I have to choose the crossing. And it might be like this, one of many cases. So this is what a projection of a small triangle might look like. Not a lot of lines going across the small triangle, just two coming from the endpoints. So this goes in, oops, that guy there needed to have a choice. Right? So now you see, this went over, then it went under, then it went under, and then it went under like that. And there's a triangle there, and the triangle move would take us to, I'll write delta for Reidemeister triangle move, and it will end up going this. Okay? And that would be a projection of one of Reidemeister's triangle moves in 3 space. Can you do it by Reidemeister moves? Well, yeah, you can, but it would require a few. Let's see. I'm going to go, I wanted to just draw it again to make it easier to look at. So can you get from here to here by Reidemeister moves? Well, they're both unknotted, right? So you just have to undo them both, right? So you could do that. You could do a third Reidemeister move. That will take this diagram to, let's just draw it again and then do the third move on it. Okay, that's a third, that's strictly speaking a third Reidemeister move. I just put this triangle and I put that triangle down there, right? And then I can do two one moves for them, and it will turn into this, and that's equal to this. So you see, from the point of view of projections of triangles, some of them are not Reidemeister moves, but they can be factored into Reidemeister moves. Others really are Reidemeister moves. For example, let's see. Suppose that I had a triangle and I had another line going underneath it in the projection, right? That could happen. And then this, by doing a Reidemeister triangle move, will end up over here. And this is just a two move. That's all it is. So I'm going to stop there and let you have some fun if you're interested in it. You can try enumerating all of the different simple triangles that you could imagine, where you have the least number of things that could go through some small triangle. You could have a triangle where lots of things went through it, right? You could have a triangle and there would be all sorts of stuff going through the triangle. But we're going to subdivide things so that we're only looking at little tiny triangles, and a little tiny triangle might have one line going through it. It might have two lines going through it, and you have to think about the end lines that come in and out of that triangle as well. And so you only need to think about small triangles, and then you have to enumerate all the small triangles, there aren't too many of them, and check what the moves are. And some of them are indeed exactly the Reidemeister moves, And others, like this one, can be done with the randomized removes. And so after you've done carefully this enumeration, you find that the randomized removes are sufficient to do everything that you need. And it's all done by thinking about the way in which curves in space can be projected into the plane. So that's a sketch of how Randomeister proves his theorem. Okay. I'm still not, oops, I didn't want to eliminate it. I wanted to keep it, right? So, yeah, thank you. So I'm still doing things from last time. Another one that I told you about from last time was the determinant item. Let's see if we can find it here. Not here, somewhere else. It was Mr. Okiai's example. Mr. Okiai's example is supposed to be unknotted. And you're supposed to do it by determ rules. And I'm going to just remind you of that. And next time I'll show you a solution to doing it by determ rules. Okay. Let me see. There was another one was Euler formula. Euler formula for link diagrams. So now what we're thinking about are things like this. What we're thinking about are things like this. And it's a graph in the plane. It could have more than one component. It's to be connected. Connected graph in the plane. There could be a link diagram, and we're not going to worry about the over and the under crossings. I just want to see what Euler's formula can tell me. So, so first of all, there are the general features of this. There is 4 edges per vertex, 4 edges per node. And we also have faces. And we can say that the total number of faces is equal to the sum over I equals 1 to infinity, if you like, of I times, of f sub I. So, in other words, f sub I is equal to the number of faces with I edges. This is 1, 2, 3, 4, 5. This is an F5. Okay. So how many faces are there with? If I went up to this diagram, I could do a count. Like here, this is 3-sided. Did I get all the, this is 4-sided, 5-sided, 5-sided, 4-sided, 3-sided. This is 4-sided, that's 3-sided, and outside 1, 2, 3, 4, 5. 5-sided on the outside. So then you see I can write down that there are, for example, the number of three-sided faces is 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. All right, like do the rest of the counts. But we do have that counting that we can do. And then I can say, I will count edges for each of these faces. And then I get I times the number of, that's the number counting I edges on a five-sided face, 5 edges for this. And I will sum those up. And I will get twice the number of edges because every edge will get counted from a face on either side of it, right? So we have this basic formula. We also have 4 times the number of vertices, 4 times the number of nodes, is twice the number of edges for the same reason. Every edge will get counted twice. So we have these 2 basic formulas that are going to be true for these kinds of diagrams. This, of course, is in general for any graph, but this one is quite specific for these graphs. So now let's see what we can do with that. Take the Euler formula. Vertices minus edges plus faces is equal to 2. Let me multiply by 4, and I get 4b minus 4e plus 4f is equal to 8. Now 4v is 2e. So this says minus 2e plus 4f is equal to 8. Now, minus 2e is expressed entirely in terms of f. And f is expressed entirely in terms of f. So I can write this as the sum on I of minus I fi, that's minus 2e, plus the sum on I of 4 fi is equal to 8. Which could be better written as the sum on I equals 1 to infinity of 4 minus I fi is equal to 8. So I get this restraint. What does this restraint say? Let's write it out. Start at I equals 1, and you get 3f1, 3 times the number of faces with 1 edge, there can be, plus 2 times the faces with 2 edges, plus 1 times the faces with 3 edges. 4 doesn't occur in the formula. And then we get negative numbers after that. 4 minus 5, 4 minus 6. So I'll put it on the other side, 8 plus, now with I equal to 5, we get F5 plus 2F6 plus 3F7 plus and so on. Okay. So you see, it tells us quite a bit. This is positive on this side. There's at least 8. That tells us that when you make a drawing like this, there must be one-sided regions, two-sided regions, or three-sided regions. They have to be there. You cannot draw a knot diagram with only 4-sided regions or only 5-sided regions. It can't be done. Furthermore, if you drew down, an interesting case is no one-sided regions, no two-sided region, right? Then there exist at least 8 3-sided regions. And you know some simple examples. For example, the Venn diagram. The Venn diagram has only three-sided regions, and there are 8 of them, right? That's the 8. That's when, so under these circumstances, this says F3, because we assume these are 0, is equal to 8 plus F5 plus 2F6 plus and so on. The Venn diagram is the simplest example of that. And another diagram that is a good example of that, one that I drew last time, I'll draw it again. That's a diagram which has no one-sided regions and no two-sided regions. So it must have at least 8 three-sided regions. It must, in fact, have 8 three-sided regions, and it does. And we saw that last time, right? So, so the Euler formula makes a very strong constraint on a lot of the things that can happen with these diagrams, and that's interesting. And you might enjoy exploring this on your own. Try drawing some diagrams and see how this kind of balance is working in playing with it. Okay, I think I've now caught up with myself in the sense of making comments about last time, and we have a few minutes left. We did. So let's talk about the following. I now want to think about generalizing coloring. And so I'm going to have an algebra. I'm going to have a label, which is an element of an algebra, and another label, which is an element of an algebra, and then a third label over here, which is going to be a product, okay? So we're going to be given an algebraic structure, given an algebra with one binary operation, which, unless I need to, I'll just write it as x, y, like that. Not associative. We'll see why in a moment. And then we need some axioms. But the axioms that we want will correspond to the Writhe moves. We're going to image the Writhe moves in algebra, where we use, where we're going to color the diagrams with elements of the algebra, just like we colored them with colors before. And we're going to use the product in the algebra for the other line, x coming up to y and crossing and turning into xy. So let's see what happens under the Writhe moves. Suppose that you had this, and this is labeled x, and this is labeled x, and this should be labeled x times x, and this should be equivalent to this, which would want it to all be labeled x. So this tells you that we want axiom number 1 is that x times x will be equal to x. That will correspond to Writhe move number 1. What about Writhe move number 2? Well, you're coming along and you're labeled X and you meet a Y, and then this becomes X times Y. And then you meet Y again and you come back out. And so you get XY multiplied by Y. But you want that to be the same as if you had this labeled entirely Y and this labeled entirely X. And so that suggests that this should be X. And there's the second axiom. X times Y multiplied by Y should be equal to X. And then we'll get to the third axiom. So the third axiom will be for the third randomized move. And now let me see. Let me actually show you that it fits this picture very nicely of the third randomized move. Right? That's the before shot on the randomized move. And this should correspond to this after shot on the randomized. I haven't been drawing the randomized move in this braided kind of way, but it's just a third randomized move, right? Triangle, shifted up, okay? And now let's say that I label this A and this one B and this one C. Then this would be BA, excuse me. B times A comes down here. This is C times A here. And then here we have C times A times B times A. Now we try it here. Here we get C times B. And then we get C times B times A. And here we get B meeting A, so this is B times A. And over here we get A. So everything worked out, over here we get A. So A is A, BA is BA, but this one should be equal to this one. And that says that CB times A should be equal to CA times BA. Now, I prefer to write things in alphabetical order from left to right. So I will write this as XY times Z is equal to XZ times YZ. So the third axiom is that it should be self-distributive. And the second axiom is that if you do it twice, you get back to where you started. And the first axiom is that if you multiply something by itself, you get itself back. And the key thing is that self-distributive axiom. That's the most complicated of these axioms and very interesting. So an algebra that satisfies this is called a quandle. The term is due to David Joyce. And it's sometimes also called an automorphic set. And some other terms. Quandle is the one we usually use. It's a funny term. Now, one thing that you can check is that RBG satisfies this. You can do it, but red times red is equal to red by definition, and that's the rule that there's one color at a crossing, right? Red times red is red, blue times blue is blue, green times green is green. Those correspond to things like green, green, this would have to be green, right? Then you can try some of the others, like red times blue times blue. Well, red times blue is green, and then you multiply by blue, and you get red back. So when you do it twice, you get the color back. And what about distributivity? Let's try it. Take red times blue times green, and we get red, green. We get red times blue is green, and green times green is green. All right. And on the other hand, what if we take red times green times blue times green? Red times green times blue times green is blue times red, and blue times red is equal to green. And these are equal. And you can try it out. You'll see it's just self-distributive. And when you check self-distributivity for all the different cases of this, you're doing all the case checking for invariance under the third randomized rule. So this systematizes in algebra everything that we were saying before. Also, RGB is not associative. Let's try it out. We take red, blue, and multiply by green, that order, and we get green times green, which is green. If you take red and you multiply by blue times green, you get red times red, and you get red. Not associative. The fact that this algebra is non-associative is very important because the relationships that we're getting out of the knot diagrams are really non-associative. Try drawing some pictures and you'll see. So that's a quandle. And now we can indicate lots of examples of quandles, many more than just RGB. Let me give you an abstract one. Example. One. Would G be any group? Should be a group, written multiplicatively. So we have G and H belong to G, and we have GH is the product. Now, I don't claim that that's a quandle, it's a group, right? But I want to define a quandle operation. So I'm going to define G star H is by definition G H inverse G. No, sorry, I wanted it the other way around. HG inverse H. Two H's and a G inverse in the middle. Try it out. G star G. By my definition, G inverse, and G, which of course is just G. Okay. What about G times H, and then times H again? So this is H times G times H inverse times H, and that's equal to H times HG inverse H inverse H, and that's equal to, remember that in a group, X times Y inverse is equal to Y inverse X inverse. And so this is equal to H, and then we get H inverse G, H inverse times H. This is the inverse of that. If you multiply these two together, it all cancels out. Then we get H times H inverse. Group multiplication is associative. So we get H times H inverse multiplied by G multiplied by H inverse H, and that's equal to G. And that's what we were supposed to get, right? Do it twice, you get back. And finally, G times H times K is going to be equal to K times the inverse of G times H. The inverse of G times H is the inverse of H, G inverse H. And we're going to multiply by K. So we get K, H inverse, G, H inverse, K. That's what happens if I do it that way. And if I do it the other way, I get G times K times H times K. And I have to do some work, and I'm going to leave it for you. Now, this is an abstract group version. Any group will give rise to a Quandle, but I want to show you a more practical one than this for our purposes. So I leave this as an exercise. We'll solve it next time or the next time. But now here's a very specific one. Let Pn equal to E. Integers Sure. Why did it suddenly decide to do that? Integers mod n. We'll work on a smaller board for a little while. We only have a few minutes. Oh, we're out of time anyway, but I want to show you this. And so I take the integers mod n, okay? So for example, we could take Z3, and this would be 0, 1, and 2, okay? Of course, 3 is equal to 0, clock arithmetic. I know you're familiar with it, so I won't go making a definition. We can talk more next time. But now I'm going to put I'm going to do the following. A times B in here is going to be equal to 2B minus A. All right? And this could be Q, this could be the algebra, or Z. You can take Z mod n, or you can use Z itself, the integers. and you define the operation to be 2b minus a. It's not an associative operation. But watch what happens when we do the operations here. We can take a times a, and we get 2a minus a, which is a. We can take a times b, and this will be 2b minus 2b minus a, and minus minus, and you get a. And if you take a times b times c, we're going to get 2c minus 2b minus a. And if we're going to take a times c, I'll do it quickly so you can try it out yourself later. Then we're going to get 2 times 2c minus b minus 2c minus a, right? 2 times this, which is 2c minus b, minus 2c minus a. Now look at these two. You get 4c minus 2c, which is 2c. And then you get minus 2b plus a. And of course, these are equal. So it's true that if you take the integers or the integers mod n, and you define a times b to be 2b minus a, you get a quandle. And for n equals 3, that is RGB. Check it out. You'll see they're isomorphic. The algebra RGB is the same as the Quandles structure on Z mod 3. But now we can do Z mod 4, Z mod 5, whatever you like. And many knots are colorable in these Quandles. And we can figure out when is a knot colorable in one of these modular arithmetic Quandles. So for example, suppose that I use 5 and try coloring the figure 8 knot. I'll take a 0 here and a 1. 2 times 1 minus 0 is 2. 2 comes down here. 2 times 2 is 4 minus 0 is 4. 2 times 4 is 8 minus 2 is 6. And 6 is equal to 1 in knot 5. And I've colored the figure 8 knot. So the figure 8 knot gets colored in a Z mod 5 quandle, and other knots will get colored in Z mod 137 or some big modulus. Every knot has a modulus. Not every knot is colorable, but it's all a matter now of some linear algebra to find out whether a knot is colorable or not in Z mod n. And at that point, we have a big collection of knot invariants that we can use. So that's a good place to stop for today.